Let's talk about surface tension. Simply stated, surface tension has to do with the ability to disrupt the surface of a liquid by applying some type of force to it. And in order to break up this, or at least alter the surface of the liquid, you are basically talking about breaking the interactions among the molecules. Right, so this resistance to break the liquid surface is ultimately a result of the intermolecular forces present in the liquid. If you have greater intermolecular forces in your liquid, it will take more energy to break the interactions, so the surface tension will end up being larger because now it requires more force for you to alter the surface of the liquid itself. Looking at the examples that we talked in the past, we have the molecule with long dispersion forces only. We have the second one with dipole-dipole forces, the third one with hydrogen bonding, and the last one with ion dipole forces. And so you have an increase in intermolecular forces going from left to right in the series. And so what you end up finding out is that the surface tension of these different molecules, at least in the liquid phase, increases. And you've probably seen examples of this in nature, in real life. You probably have seen droplets of water, either on your car or some other material that has been painted, in which the water is present in the form of these droplets. Same thing for leaves. You can actually see formation of droplets of water as opposed to just the water spreading out as much as possible. And the reason why is because the surface tension within the molecule, as a result of the intermolecular forces of attraction, tries to maximize the amount of interaction within the molecules in that compound. And the best way to do it is to attain a spherical shape, because that will maximize, geometrically speaking, how many contacts you have among the molecules in the liquid. And also, the more traditional example is that of the daddy long leg walking on water. The force that the daddy long leg insect supplies or provides onto the water is actually less than the surface tension of water, which allows the insect to actually walk on it. And also, the fact that the legs are so long allows the insect to spread its weight quite efficiently throughout a very great surface area compared to the actual body of the insect. So the spread out um, of weight in such a large surface area ultimately makes it such that this object, the insect, is less dense than water itself. So the surface tension of water can actually withstand the weight of this insect. Alright, now a different property, which is somewhat similar, is known as viscosity. Now viscosity ultimately has to do with liquids flowing out of flasks or just flowing in general. And if you look at this example right here, this picture, it's actually 5 test tubes, all angled exactly at the same degree, but they have different substances in them. And what you can see is a difference in the tendency to flow out of the flask. Some of the substances flow out, quite efficiently. Like the moment you tilt it, you're already having the liquid pouring out. Other ones, you have a much more subtle stream. The third one here, is sort of like flowing out of the flask, but at a very slow pace, and the other ones don't even make it out. And the reason why is because the intermolecular forces present in these liquids are different. In particular, viscosity, which is the resistance of a liquid to flow, is simply a result of the fact that as the intermolecular forces of attraction increase, you are going to have your molecules with less a tendency to be removed from each other or breaking apart from each other, and so that will prevent the liquid from flowing away. It's kind of similar to the surface tension, but here we're thinking about flow as opposed to disrupting the surface of the liquid. And so increasing the intermolecular forces will increase the viscosity. And as an example, you can see here, you have your simple molecule, your carbon oxygen molecule with hydrogen bonding. Then you could increase that by adding an additional OH bond, which gives you more hydrogen bonding. You could have more OH bonds in the molecule right here, and you could have the same amount of H bonds, but then as a result of the fact that you have more dipole-dipole forces and that the molecular weights are increasing, the last molecule overall will have the greatest amount of intermolecular forces. So the viscosity you will predict to increase from left to right in this series. You have great intermolecular forces, therefore your viscosity is higher. And unlike, our beloved anti-hero, well, it's not really an anti-hero, he's just straight out villain. Pennywise, he'll tell you you'll float too, and I say, sorry, Mr. Pennywise, only if the intermolecular forces say so. Alright, now there's one more aspect in terms of physical properties that we need to mention, and it's known as volatility. And you gotta be very careful with the terms. They both start with V, but as you'll find out, the tendencies in terms of intermolecular forces are different for these two things. Viscosity is not at all the same thing as volatility. Viscosity is the resistance of a liquid to flow. How much does the liquid can resist to flow? Whereas volatility is actually dealing with the tendency of a liquid to evaporate. The more volatile a liquid is, the easier it's going to be for it to turn into the vapor phase. Alright, so we're basically looking at how much gas we have present out of that liquid. And if you consider what's going on right here in terms of the molecular interactions, liquids, generally speaking, are closer to each other than gases are. Gases are able to expand, and usually they don't even retain a structure of their own, right? So they just expand as far as the volume of the container allows them to. But the liquids, it doesn't matter how big the container is in which they are present, the liquids will have a distinct volume of their own. So generally speaking, liquids are closer to each other than gases. But that also means that gases, because as a result of being farther away from each other, gases will have to have had their intermolecular forces broken up. And specifically, you will have the liquid have its intermolecular forces broken up to turn into a gas. Now, if volatility is the tendency of a liquid to evaporate, and the gas is already what you have after you break apart the interactions, what this is basically telling you is that if you increase intermolecular forces, it will be harder for you to break the interactions in the liquid, and therefore you have less gas. As a result, increasing the intermolecular forces is the same thing as saying that the volatility goes down. And this is why you have to be careful with viscosity and volatility. If you increase intermolecular forces, viscosity goes up. However, if you increase intermolecular forces, volatility goes down. So be very careful with that. So in the series right here, where you have long dispersion forces, followed by dipole-dipole, followed by hydrogen bonding, and then more hydrogen bonding, the intermolecular forces are increasing, going from left to right. That means that the volatility will decrease, meaning that water in this series ought to be the least volatile of the substances, whereas propane is the most volatile. In fact, at room temperature, water is a liquid, whereas propane is actually a gas. Alright, on the next video we'll talk about phase transition diagrams and heat.